Welcome to episode 3 of Let's Talk About Data, where we break down the art and science of becoming an elite AI engineer. Today, we're taking you from zero to hero and setting up a powerful, production-ready environment with Linux, Git, Python, and Docker. This is the invisible backbone of real-world AI workflows. You've probably heard the phrase, "Well, it worked on my machine." In AI engineering, that excuse doesn't cut it. With complex models, specialized hardware, and distributed teams, environment setup isn't just a detail, it's mission critical. It determines whether your models can move from concept to deployment smoothly and reliably. Let's start with consistency and reproducibility. In AI workflows, reproducibility isn't optional, it's essential. You need to ensure that an experiment run today can be replicated next week by someone else on different infrastructure. That only happens with standardized environments. The solution? Containerization. Tools like Docker and orchestration platforms like Kubernetes ensure your code, dependencies, and runtime are all encapsulated and portable. You're not just writing code, you're packaging a system. When done right, deploying your project becomes a seamless, one-command operation, not a scavenger hunt of broken dependencies. Next, efficiency and speed. In AI, iteration is everything. You're testing hypotheses, tuning hyperparameters, and working with enormous datasets. An optimized environment enables rapid experimentation. You need access to the right compute resources, especially GPU acceleration. You also need shared, high-throughput storage to handle training data and artifacts. Most importantly, environment setup lays the groundwork for automation. ML pipelines, which orchestrate everything from data cleaning to deployment, depend on stable, predictable environments. With pipelines in place, you spend less time configuring and more time innovating. Fast failure and iteration become your allies. But the ultimate test of any AI system is how it performs in production. This is where environment setup makes or breaks reliability. You need real-time monitoring, what professionals call telemetry, to ensure performance, detect anomalies, and enforce responsible AI practices like fairness and bias tracking. You'll face constraints like latency, hardware variability, network bandwidth, privacy requirements, and cost. A well-architected environment accounts for all these. Security, too, is non-negotiable. Integration with identity providers, encrypted data pipelines, firewall configurations, these aren't afterthoughts. Smart teams create staging environments that mirror production, where models can be validated thoroughly before going live. Deployment pipelines, with support for rollbacks and canary deployments, help teams move fast without breaking things. Managing your environment is a reflection of professionalism and craftsmanship. Neglect breeds entropy. Small mismatches snowball into brittle systems that nobody understands or wants to maintain. In today's AI teams, often made up of data scientists, ML engineers, and DevOps professionals, a shared environment is the glue that keeps collaboration frictionless. It's about building systems that last, that scale, and that are resilient to change. Investing in your environment isn't overhead, it's an act of respect for your teammates, your users, and your future self. So the next time you start an AI project, remember, the environment isn't the backdrop, it's the foundation. If this gave you a fresh perspective on why setup matters in AI engineering, hit that like button and subscribe for more insights into real-world ML ops, data science, and machine learning engineering. Drop a comment. What tools or strategies do you use to manage your ML environments? Now, we're exploring a question that comes up a lot. Why is Linux so dominant in the world of AI engineering? Now, if you're just building models on your laptop, your OS might not seem like a big deal. But as you step into the real-world engineering side of AI, where things need to scale, deploy, and just work, the operating system becomes a critical part of your stack. Let's look at the modern AI engineering workflow. It's far more than just training models in a Jupyter notebook. You're managing data pipelines, deploying models as APIs, monitoring performance, scaling across clusters, and integrating with enterprise infrastructure. This isn't just experimentation, this is engineering. And when it comes to handling this level of complexity with stability, flexibility, and efficiency, Linux leads the way. So why Linux? First up, consistency and reproducibility. Machine learning workflows depend on being able to reproduce results exactly, whether it's training a model or deploying it across multiple environments. That's where containers come in. Tools like Docker and orchestration platforms like Kubernetes run natively on Linux, and they rely on it for speed and reliability. Whether you're training locally or deploying globally, Linux provides the consistent foundation that containers need to perform seamlessly. Next, high-performance compute. Training deep learning models takes serious horsepower, and that often means GPUs. The best drivers, libraries, and frameworks for GPU acceleration are built and optimized for Linux. If you're training large models or working with high-throughput pipelines, Linux gets you closer to bare metal and gives you tighter integration with the tools you rely on. Third, automation and pipelines. MLOps is all about automation, from data pre-processing to model training to deployment and monitoring. Linux offers unparalleled flexibility for scripting and orchestration. Pipelines run as containers, jobs are triggered via cron or APIs, and everything plugs into powerful open-source ecosystems. The command line culture, shell scripting, and Unix principles make Linux a natural home for complex workflows. Now, you might be thinking, I can run TensorFlow on Windows, and you're not wrong. macOS and Windows both support many ML libraries. But here's the kicker. The closer your development environment is to your production environment, the fewer surprises you'll face later. And since production often runs on Linux, whether on premises or in the cloud, working within Linux from the start leads to smoother transitions, fewer bugs, and better scalability. It's also about alignment. The open source tools driving AI, from PyTorch to TensorFlow, from Airflow to Kubeflow, are born in Linux. While they may offer cross-platform support, the native development, testing, and deployment environments are Linux first. By choosing Linux, you're aligning with the direction the industry is already moving. So let's recap. Why does Linux dominate AI engineering? Reproducibility, thanks to containers. Performance, especially with GPU acceleration. Automation, seamless scripting and orchestration. Scalability, built to run across clusters and clouds. Alignment, with the tools and infrastructure AI depends on. If you're serious about deploying real-world machine learning systems, Linux isn't just an OS, it's the infrastructure language of modern AI. If this video helped you understand the real advantages of Linux in AI engineering, don't forget to like, subscribe, and leave a comment below. What's your preferred OS for AI work, and why? So far, we explored why Linux dominates AI infrastructure. Now, we're taking the next essential step, setting up Python and using virtual environments, a critical foundation for every AI engineer. Whether you're on Windows, macOS, or Linux, these are the first moves you'll want to get right before diving into model training, data pipelines, or deploying AI solutions. When it comes to AI, Python is the industry standard. Why? It's all about the ecosystem. Python gives you access to an expansive suite of powerful libraries. NumPy and Pandas for data handling. Matplotlib and Seaborn for visualization. Scikit-learn, Keras, TensorFlow, and PyTorch for machine learning and deep learning. Whether you're building a recommendation system, fine-tuning a language model, or just cleaning raw CSV files, Python is at the heart of it all. But here's the problem. Different projects need different dependencies. Project A uses version 1.0 of a library. Project B, version 2.0. If you install both globally, you risk breaking one project while fixing another. This chaos is known as dependency hell, and it's one of the biggest productivity killers in AI development. Enter virtual environments, your best friend in avoiding conflicts. A virtual environment is like a personal sandbox for each project, with its own set of dependencies, isolated from your system, Python, and other projects. Here's how it works. This creates a folder called My Projectinf. It's your project's own little world. To activate it, now your terminal prompt changes, indicating you're inside the environment. Every pip install you do now is contained within this environment. No cross-contamination, no surprises. Project A and Project B can happily coexist with their own dependencies. But local environments are just the beginning. In AI engineering, we eventually scale beyond our laptops, deploying models, automating pipelines, and training across clusters. This is where containerization comes in. Containers, like those created with Docker, wrap your code, libraries, and runtime into a single portable unit. They provide true reproducibility. The code you test on your machine, it will behave the same on another machine, or even across a Kubernetes cluster. If you've defined your environment in a Docker file, your container will install exactly the libraries it needs, and nothing more. It's like a virtual environment, but for production-scale workflows. The good news? Many platforms today handle this environment setup for you. Google Colab gives you a free cloud notebook with many popular libraries pre-installed. Red Hat OpenShift Data Science offers containerized Jupyter notebooks with everything configured out of the box. Kubeflow lets you run notebooks that tie directly into your AI pipelines and deploy to production seamlessly. These tools abstract the underlying complexity, but understanding virtual environments is still critical. It prepares you for building clean, scalable, and production-grade AI systems. To wrap it all up, Python is your go-to language for AI. Virtual environments keep your projects clean and conflict-free. Containerization ensures consistency at scale and in production. Whether you're starting on your laptop or orchestrating a fleet of training jobs in the cloud, these are the foundational steps that every AI engineer must master. If this video helped clarify how to manage your Python environments, don't forget to like, subscribe, and hit the bell icon for more weekly insights. Drop a comment below. What tool do you use to manage your Python environments? So far, we've laid the groundwork. Linux, Python environments, essential tools. But before we even write a line of machine learning code, there's one tool that every serious developer, especially in AI, needs to master: version control. And now, we're diving into the core of that: Git, and platforms like GitHub that make collaboration, traceability, and scale possible in AI engineering. So what is version control? Think of it as undo on steroids. It records every change made to your files, lets you rewind, branch off, test ideas, and track every line of evolution, no matter how messy your code gets. At the heart of this system is Git, the gold standard for managing codebases. Git isn't just for developers, it's a vital asset for data scientists and AI engineers who need to maintain clean, testable, reproducible code. Now here's the twist for us in AI. Our input isn't just code, it's code and data. And your final output, your trained model, is deeply dependent on both. You could run the same training script twice with different datasets and get completely different results. In fact, even a subtle change in data, like shuffled rows or an updated label, can change the model's behavior. This makes reproducibility a major challenge. If you can't recreate the exact environment, code, and data, you can't debug accurately, compare model versions, or guarantee reliability in production. For your code, Git is your best friend. Every script, every Jupyter notebook, every config file, you commit them all with meaningful messages. You create branches to test new ideas without touching your production code. You revert bad changes, collaborate with teammates, and keep a clean, inspectable history of how your models were built. That's not just neat, it's non-negotiable in professional AI development. But let's talk about the elephant in the room: data versioning. Here's the truth: Git is not optimized for large datasets. It's perfect for text, not for binaries or multi-gigabyte CSVs. Trying to shove entire datasets into your Git repo? That's a fast track to frustration. Instead, AI engineers use specialized tools that apply Git-like principles to data. These tools track changes, manage history, and keep your data pipeline reproducible without bloating your repository. This practice ensures that the exact data version used in any experiment can be retrieved and compared, critical for auditing models, debugging, and even compliance. Now, let's zoom out to the ecosystem. Platforms like GitHub, GitLab, and others act as centralized hubs for your code. This is where your team collaborates, your CI/CD pipelines run, and where open-source projects share the exact notebooks and scripts used to build published models. For AI engineers, having your code on GitHub is about transparency, teamwork, and traceability. It's your project's command center. By combining Git for code and the right tools for data, you gain the superpower of reproducibility. You can always answer the question, what code version and what dataset version created this model? That's professional-grade AI engineering. So to wrap it up, Git is non-negotiable for versioning your AI code. Data versioning is just as critical, and you need tools purpose-built for it. Platforms like GitHub turn your workflow into a scalable, collaborative, and reproducible system. These practices aren't optional. They're foundational to modern ML ops, reliable model delivery, and working as a team in the real world of AI. If this helped you gain clarity on the role of Git in AI engineering, give it a like, subscribe for more deep dives, and drop a comment below. How do you manage versioning in your ML projects? Now, we're diving into a tool that has quietly become the backbone of modern AI workflows, Docker. You've probably heard of the phrase, "It worked on my machine." But when it comes to AI engineering, where you've got GPUs, CUDA versions, complex dependencies, and team collaboration, that excuse just won't cut it. Let's talk about why containerization is the solution, and why every serious AI engineer needs to master Docker. Your Python code might rely on specific versions of TensorFlow, CUDA, scikit-learn, maybe even obscure system-level dependencies. It runs perfectly on your system, but completely fails on your colleague's machine, your server, or your production cluster. That's because you're not just shipping code, you're shipping an entire environment. And that's where traditional setups fall apart. Containerization solves this by packaging your code, its dependencies, config files, and runtime environment into a single, portable unit, a container. Unlike full-blown virtual machines, containers don't carry a complete OS. They share the host's kernel, making them lightweight, fast, and isolated. You can think of it as shipping your app with its own little operating system, without the weight of a full OS. So whether it's your dev machine, a test cluster, or a production server, that container behaves exactly the same. No more surprises. No more. It worked on my machine drama. Docker is the tool that makes this happen. You define a container using a simple text file called a Docker file, basically a blueprint for your environment. You start with a base image, like Python 3.10, or an image with PyTorch already installed. Then add your code, install your packages, and configure anything you need. Once it's defined, Docker builds an image, a snapshot of your app and its environment. That image can be pushed to a registry like Docker Hub or your cloud provider. From there, it's accessible from anywhere. So, why is this game changing for AI? Reproducible training. When training deep learning models, reproducibility is non-negotiable. Containers let you freeze your environment. Train today and you'll get the same results tomorrow or 6 months from now, even on a different machine. 2. Standardized notebooks. Platforms like OpenShift run Jupyter notebooks inside containers, preloaded with TensorFlow, PyTorch, or anything you need. Teams can even build and deploy custom notebook containers so everyone works in an identical environment. 3. Scalable model serving. Serving models? Docker containers are used to deploy them through TensorFlow, Serving, TorchServe, or Seldon Core. Want auto-scaling and endpoint security? Just wrap your model in a container and plug it into a Kubernetes platform. 4. Automated pipelines. With tools like Kubeflow pipelines, each pipeline step, from data prep to model training to deployment, runs in a dedicated container. That means isolated, parallelizable, and reproducible steps. Containers are the glue between experimentation and production. They allow your ML stack to scale, share, and deploy without friction. To wrap it up, Docker and containerization aren't just nice-to-have tools. They're essential for AI engineers working in real-world environments. Containers solve the dependency nightmare, enforce consistency, and power the platforms that define modern ML ops. If you're serious about scaling AI from notebooks to production, learning Docker is non-negotiable. If this video gave you clarity, give it a like, subscribe to Let's Talk About Data, and tell us in the comments, how are you using containers in your ML projects? Before you build pipelines or deploy models, you need to write code, explore your data, and iterate fast. That's where developer productivity tools come in, tools that help make the initial stages of machine learning efficient, collaborative, and most importantly, reproducible. For many data professionals, Jupyter notebooks have become the go-to environment for data exploration and model development. Why? Because they're more than just code editors. They're interactive documents that blend code, visualizations, and narrative. You can run individual cells, tweak logic on the fly, visualize results instantly, and document your thinking as you go. That level of interactivity is a game changer for data wrangling, feature engineering, and rapid prototyping. Modern platforms recognize this power. You can now launch hosted Jupyter environments that are tightly integrated into your infrastructure, running on containers, backed by scalable compute, and connected to production-grade tools. One of the biggest advantages of these hosted environments is consistency. Pre-built container images come loaded with popular frameworks like TensorFlow and PyTorch. This eliminates dependency issues and gives every team member a consistent, battle-tested environment. Even better, you can spin up different workbenches tailored for different needs, from lightweight CPU environments to GPU-accelerated setups for deep learning. It's productivity with scalability baked in. That said, notebooks alone aren't enough for production. They're amazing for experimentation, but less ideal for version control and automation. That's why modern ML ops platforms let you turn notebooks into pipeline components. With a few tweaks, you can embed notebooks into an automated workflow, where each step runs in a container, tracks metadata, and logs outputs. Some environments even offer drag-and-drop pipeline builders that let you visually stitch notebook steps together, making the transition from experimentation to production as seamless as possible. So where do traditional code editors like Versus Code fit in? While notebooks are ideal for exploration, Versus Code excels at writing modular, maintainable code, especially when you're building reusable components or working with version control systems like Git. In practice, most AI engineers use both, notebooks for fast iteration and insight discovery, and editors like Versus Code for structured development, debugging, and team collaboration. Together, they form a powerful workflow, from idea to deployment. Here's the big picture. AI engineering isn't about choosing one tool over another. It's about using the right tool at the right time. Notebooks accelerate discovery. IDEs bring structure. And MLOps platforms bring it all together, enabling automation, reproducibility, scalability, and collaboration across teams. From interactive exploration to containerized pipelines, from local experiments to production services, these tools form the backbone of a robust AI development lifecycle. If you want to build intelligent systems that scale, mastering your development environment is just as important as mastering your models. So, what tools are part of your AI engineering stack? Drop them in the comments. If this video helped you connect the dots, give it a like and subscribe for more deep dives into the world of data, AI, and production-grade ML. Before we wrap, here's your AI engineering environment checklist. Linux or WSL setup. Python plus PyAF plus Vend/Conda ready. Git and GitHub workflow active. Docker installed and tested versus Code plus Jupyter configured. With this setup, you're ready to tackle any AI project. In the next episode, we dive deep into Python for AI engineers, not just syntax, but how to think like an AI architect. Don't miss it. Like, comment, subscribe, and keep building.